All right, recording's on.
All right, awesome. Thank you. Well, welcome everyone. So this week we're talking about chapter 7, which is about transactions. And I was thinking about this chapter. It's really talking about this idea, this concept, this abstraction of a transaction, and how having transactions at the lower level allows you as an application programmer, whatnot, to simplify your thinking, because there's all these use cases that you don't have to worry about, that they're taken care of for you by the transactions. And so in thinking about this chapter, I think this week, what I've done is, for the notes, I've kind of taken them at a slightly higher level, talking about what are the key concepts. So what are the race conditions that can happen if you don't have protection? And then, of course, the book talks about the different ways that they mitigate this, how they're implemented. And I think the examples in the book are really good. I didn't reproduce those in the notes, but so if people have questions, certainly I've got the book open. We can flip to, we can look at some of the examples, things like that. But so that's kind of how I was thinking about going through the discussion, is just sort of a couple prerequisite ideas, and then just kind of going through the different race conditions. So, but before I dive in, I just wanted to check, did anybody read the chapter and have any particular questions, any things in particular that you want to make sure that we hit on this week? All right. So feel free at any point just to shout out if you have any questions, or if there's anything you want to drill in deeper. And then if for whatever reason your microphone's not working, then I'll just ask Ryan to monitor the chat, since I don't know. I really love Zoom, but sometimes the popping up a chat window doesn't work very well while you're presenting. Okay, so the discussion of transactions, sort of, as I said, it starts about saying, hey, here's a set of guarantees that I'll mostly just call it a database from here on out. It doesn't necessarily have to literally be what we think of as a database, but any system that's storing data. Guarantees that the database can provide about your data. And so the old acronym thing that people have been talking about for, like the book says, whatever, 40, 50 years, is ACID. And so there's 4 components of that acronym. So the A stands for atomicity. And so that means that if you're doing multiple things, in particular, if you're doing multiple writes, then either every one of them will succeed or every one of them will fail. So the classic thing is, if you're transferring money between 2 bank accounts, if they take out $100 from bank account 1 and they put $100 in bank account 2, you don't ever want to be in this situation where the first write that takes out the $100 from your first account succeeds, but the second one that doesn't put the $100 back in your second account fails. You'd prefer that the whole thing worked. You can live with if the transfer doesn't happen at all, but you really don't want that in between state. So atomicity is pretty important, and that's generally pretty straightforward. It was kind of interesting to see this discussion about consistency. And so the way the author presented it, he said, hey, consistency is really about some properties of your data that you think are invariant. So in accounting, you got your balance sheet, and things should balance. And there's other kinds of properties that you could have. And basically what he said is that the database doesn't know about these properties. The database can't preserve these properties. It's really up to the application to create transactions, such as you're transferring money from one bank account to the other. I'm going to wrap those 2 steps inside a transaction. It's totally up to the application to decide what needs to be in a transaction. And so consistency is actually a property of the application. It's not a property of the database. And so C shouldn't really be part of ACID. It should just be AID. I thought that was pretty funny, since like I've been hearing about ACID for years and years. I guess it just made a better sounding acronym than AID. So isolation is if you've got some operations you're performing, is it going to act any differently with you being the only user on the system doing everything all by yourself versus other stuff is running at the same time? And in particular, overlapping with when you're doing your reads and you're doing writes. So as we'll see, the fullest level of not interfering with each other is going to be serializability. And so that's where you could take the things that happened, and even though many things overlapped in time, you could imagine a different timeline where if you did things one at a time serially, there's an ordering in which you could say, I got the exact same results doing it that way that I did in reality when things were overlapping and things happened. And so all these race conditions that we're talking about, that's when you get something that's different, where it's not possible to order different people's operations in a way that you get the result that you got. So the result is based on this concurrency, it's based on that level of instability. So pretty much the rest of this chapter is all about isolation. And then finally, I thought it was interesting that the chapter notes that durability, at a very simple level, we think of it like, oh, okay, so we wrote it to the disk, that was successful, so we say we're going to return success. It's done. It's durable. But technically, if you think about it, disks fail, RAID arrays fail. No matter what you have, you're never 100% safe. So there is always this extreme case where the application returns to you, hey, your write was successful, and then right after that, all heck breaks loose. And in fact, even though you received the acknowledgement that your write was successful, the data was actually lost. So it's, the more redundancy and all that stuff you have, the harder that is to happen, but nevertheless, it is possible. So that's the quick overview of, sorry, I'm just looking for one other thing I have in my notes. I'm trying to, oh, there it is, it's down here. Okay. So that's an overview of ACID and the different things we're going to talk about, primarily isolation. So any questions? Anybody have anything at this point? All right, so you guys are just chatting about the stock market or something? All right, there's a short section here that talks about just the relationship of multi-object operations and this idea of transactions in ACID. And basically, the gist of it is that when we talk about transactions, we're generally referring to multi-object things, like you do a write to the balance on bank account 1, and then there's a separate entry in your database that has the balance for account number 2, and so you're writing to 2 different objects. But he explains that if you think about it, there are other cases that sort of look similar to 2 different objects, even if they're not technically. So example would be if you're writing a large JSON document, it can actually take time, and on a disk, that document can span multiple blocks on a disk. So you could have a failure halfway through, and you really wouldn't want to have a situation such as, you have the first half of the new version of your JSON document, the second half of the old version of your JSON document, and basically it's just going to be a corrupted file. So you can think about some of these other things requiring this atomicity, not usually not as much requiring isolation, but some of these properties of ACID. So ultimately, the idea behind a transaction is because stuff's being abstracted away from you, it's that the operation will either happen in its entirety, or it will be anything that was done partially will be undone. So you can just think of it as it's all or nothing. And so that means that it's safe to retry if you get an error when you're doing something inside of a transaction. You don't have to worry about that. Like if you're incrementing things that they're just going to keep incrementing multiple times. No, it's either going to happen once or it's going to not happen at all. But I thought there was 2 interesting comments in this section. So I don't know if any of you do sort of full stack development, but a lot of people use these object relational mapping functions within within their programming language. So Java, C++, if you've got classes that you've defined, those classes may not map to a single object, say in your relational database, a single table. So if you define, whatever car as a class, then you may have multiple things in there. You may have a table for the engine, for whatever, the body, the wheels, the whatnot. And so you're actually you're having to write to multiple tables. And so behind the scenes, you actually need this ORM layer to be smart about how it's handling transactions. And the big takeaway from this chapter is that, generally speaking, when you install a database, when you install a product, it is not going to be doing serializability. It's going to be a weaker level that has better performance. And so if you just think, oh, I installed this software, it says it's ACID compliant, I'm coding, I've got this object relational mapping layer that handles things for me. In fact, you do have race conditions that are possible. So for me, that's the real big takeaway, is don't just assume that because your product says it's ACID compliant and you're using transactions that everything is solved. Okay, so then the rest of the chapter talks about weaker isolation levels, and the goal of these is to have better performance. Typically, better concurrency. It's not so much about response time, it's usually, about concurrency, which ultimately, if things get blocked, that does lead to response time, but that's the main issue. So in the notes, I've sort of highlighted here with the red text and the yellow highlight, whenever we come across one of these 6 race conditions that are being explained in the text when we talk about the different isolation levels. So if you kind of want a quick reference, then you can see them here. And also at the very end of the chapter, the author does a nice job where he just recaps, here are the 6 different race conditions. Are people familiar with the term race conditions? Because it's like, I heard the term, but like it occurred to me, I tried even like Googling to see what's the etymology of the term, and I wasn't able to find anybody who explained sort of like where this term came from.
I could give an example. I know.
All right, yeah, would you, Keegan?
Okay, sure. An example of a race condition. So let's say you had a e-commerce store, and you're buying a car, right? Or you're buying something on this e-commerce store. You send a select statement. You do an insert statement with SQL, but you, at the same time, you also want to view your order. And what could happen is that it views your order before the process was fully transferred. So the ordering of the SQL statements, the ordering of the transactions could be out of order. So you would essentially, it would say, oh, you didn't actually purchase this, but maybe like part of the SQL statement, like maybe the part with your bank, maybe money went out of your bank account, but it doesn't show up in the website. So the idea is that if it doesn't, the race conditions is when things are out of order and it sort of breaks stuff. Does that help?
Yeah, thanks, Keegan. Yeah, so that example would be like my mother-in-law sometimes she'll come over for dinner and she'll say, oh, I was on some site and I was trying to buy something and I was getting these weird errors and I wasn't sure what was happening. So either I didn't get it or I bought 3 of them by accident or somewhere in between. Something like that. I think the term race condition might actually come not from like computer software, but like electronics. So if you imagine a circuit board and you've got different wires where your inputs are going into a certain part of the logic, the reality is, right, electricity doesn't travel through wires instantly. There's speed. And so since it's largely a 2-dimensional circuit board, if things, have to kind of go around other things. If you have a longer wire and a shorter wire, then the signal in the longer wire will arrive delayed. And so like kind of a made up example I was thinking about is, imagine you have some logic that like decides, the outcome of rock, paper, scissors. And so if you start out with two people and they both say rock, all right, so then basically your logic's going to say it's a tie. Now, if you say, 1, 2, 3, shoot, and then one person switches to paper and the other person switches to scissors, if the scissor signal comes a lot faster than the paper signal, then what it'll look like is that the first person is still on rock. And so your little rock, paper, scissors logic could actually say like, oh, look, it's rock and scissors. And so therefore, the person with the rock won a game. And then, a fraction of a second later, then finally when the paper comes through, and then it says like, oh, well, scissor beats paper. And so then actually the scissor person won a game. And so whereas it should only be recording one new game that the person with scissors won, it could actually be recording that that there was a rock versus scissors game, and then that was followed by a paper versus scissors game. So then you can imagine, like I sort of tried to imagine that this is the actual etymology of the term, then you've got little electrons on these longer and shorter paths racing each other to get to the next, the next gate, the next circuit. A little bit of terminology. So the next thing I said is you should be familiar with the terms committed and uncommitted. They get used over and over again in this chapter. So when a transaction completes and it's successful, then that transaction is said to be committed. In the meantime, while the transaction's ongoing, then you talk about the writes that have happened as uncommitted. And so without getting to the implementation details, you have this funny idea that, the bank account used to say $1,000 and now you're taking out 100, so it's supposed to be 900, but there's the possibility that the transaction will succeed, and that's fine, the 900 is permanent. But there's also a possibility the transaction will fail and you need to go back to the 1,000. So how can you go back to the 1,000? In some way, you need to be sort of preserving extra information. You can't just simply overwrite it. The other thing that's mentioned in this chapter is locks, and I kind of like double checked. I'm pretty sure the author doesn't explain locks at all, and so I don't know if I put two references in here, sort of a simple one from Wikipedia, and then sort of this deeper one I was able to find. So is everybody here familiar with locks? Does anybody want me to sort of explain this concept a little bit?
Yes, please.
Okay. So I'm just going to use sort of the single node relational database. That's where I have a lot of experience as the way of explaining, but you can generalize it to other situations. So in a relational database, you can have a table. So you can have, let's say, on an e-commerce site, you have a table of products, a table of customers, a table of orders. And you're going to have a primary key. That's the key where you look up. So you have a customer ID. That's the key for your customers. You have an order ID. That's the key for. So in a simplistic scenario, basically, in parallel with all the data that you have in the system, you can have locking information that you're storing, which is metadata that's saying whether or not somebody is busy using a particular piece of information in your database. And based on what we do is we create different kinds of locks. And depending on the kind of lock, then what'll happen is before you will do a read or a write, you will actually look to see if somebody else has a lock. And then you can set up the rules as to which operations will force you to wait and which ones will allow you to go ahead. So like a very simple scenario, which we're going to come up to, is you can say if somebody's going to write something, in order not to have two people stepping on each other, if you see that somebody's trying to write to bank account number 2, then you're not allowed to do the write. You have to basically wait until that lock gets taken away. And then once you see that lock's taken away, that means the other person's done. Now you can go ahead and do what you were going to do. Okay. And it gets a little bit more complex if you have like secondary indexes and other things, but essentially that you can just think of it as the database or the operating system at a low level is implementing this other mini database of metadata. And you can assume that those operations themselves have their own abstraction of atomicity and whatnot. And so that basically if two people request a write lock on bank account 2, the database or the operating system guarantees that it will never be the case that both of them get yes on that lock. It guarantees that only one of them will say, yes, you got a write lock on bank account 2, and the other one is told, nope, somebody else already has a lock on bank account 2. And so that's just taken care of you by the system. And so what we'll see is that by having different kinds of locks and rules between how they interact, which ones block which other ones, then you can, if your locking system is relatively fast, then you can fairly quickly just look up and say, hey, is anybody using bank account 2? No, great. I want it, give me a lock. I'm going to do my thing. And then when I'm done, I'm going to say release that lock. So does that work? Anybody have any questions about locks?
Yeah, that's fine. Thank you.
Actually, I have a question about how all of the things that you just talked about are being reflected exactly in like a very popular kind of holiday shopping season, right? So how is this even related to that? Like if many people put their stuff into the cart, but not necessarily checking out right away, and how long the retailer will have to keep it at that point, and how do they also want to maximize the sales without making that just stay in the cart for too long?
Yeah, so there's two separate issues here. So the one issue that I can speak to with a fair amount of confidence is if you have only 100 Tickle Me Elmo toys left, and you want to know how many people have that in their cart, whether even though they haven't actually finished their purchase yet, you would use the kinds of things talked about in this chapter. You would use locks to have a definitive, accurate number of people who have that toy in your shopping cart. Okay? There's this whole separate problem that says, if it's a really popular toy, how long are you going to let somebody hold it in their shopping cart and prevent somebody else from buying it? I don't know if anybody else on the call knows about sort of what sort of algorithms, what heuristics, people use. I know I've seen like Ticketmaster, they're very explicit about it. They'll say, hey, we're holding these tickets in section 219 for you. You have 60 seconds left to complete your purchase, or we're returning it to, the pool where other people could buy them. And they're very explicit about how long you have to finish buying, or else you're going to, lose hold of them. I don't know, does anybody else?
It is something that is very situationally dependent. Like, as you said, in Ticketmaster, like they can really only sell one of those. Okay. Technically, the same thing happens in airlines. You're only selling one of those, but airlines get oversold all the time, right? So that in the system, they a lot of the time will, some of it's built in where you allow for extra sales to happen. Sometimes you kind of put in some of these guarantees where you're not allowing extra sales to happen. And so that's why I was like, it's really situational. I do think it's interesting that it's like a lot of the time people do play it loose. I think even on the sales engines, even with like say Amazon, they'll play it loose when they're like, oh, only 6 left in stock. Well, if 2 people happen to cart it and buy it at the same time, they're like, okay, we'll just give, like, we have another process for dealing with that, right? Like, we'll be like, oh, we're so sorry, here's your money back plus some extra to make you happy. Like it's not a technical solution. And I think that happens a lot more than we actually think it does. The other thing is, like, sometimes you can let stuff sit in, like, they'll take the approach of being like, oh, we'll let it sit in the cart, but if that's not when we actually say we're actually committing to it, right? It's when you actually do your purchase that we're really committing to it. So we may have 5 of these. We let 1,000 people put it in their cart, but the first 5 people actually say, you know, checkout are the ones we really follow up with, right? Everybody else, oh, when they click on checkout, we'll be like, oh, sorry, your cart's changed. So.
And I had a very recent experience of checking out for 2 decorative pillows, and for whatever reason, the transaction went through. But then days later, they sent me a notice and say, sorry, we have to cancel one of your pillows. And I was like, and why did you not cancel all of my pillows? Because I need 2, right? and now they literally send me 1 pillow. And that's the situation I was really confused about. Like, why did they not know when I check out that it's already not available? I guess there's a delay. Yeah.
About airplane
Or-
tickets.
Or their business process just choose to send you product so they can make money rather than canceling your order, because it's a sale.
Right, but you also need to think about customer satisfaction and how long it's going to make you money if the customer is not happy.
Right. But
Yeah.
most
Yeah,
companies
if they're a good
actually
company,
think
you
about
should
that.
be able to tell them they did this to you, and hopefully they'll, you know,
Yeah,
they'll take
they're
care of it.
definitely willing to take the risk that they're going to be in some of these
That's right.
situations, and they
Mhm.
think that they can satisfy the situation in a way that doesn't lose them too much business, right? And when you think about it, the number of times this actually comes down is actually pretty rare on a lot of cells, right? It's only like, okay, yes, the day after Christmas sales become a thing. Ticketmaster becomes a thing. So there's a lot of stuff focused on there, and even then, the compensation may just be adjusted. So it's like, oh, it's the day after Christmas, so offer them 2x back rather than, you know, only 1.5x back, right? Like, there's a lot of stuff that just happens not in the actual technical realm, which is funny.
Yeah. Right. Instead of solving it with the computer, just ask for forgiveness later.
Yeah.
Yeah.
Right, so Becky,
Actually,
I think-
you know,
I
my
think that-
wife complains. Oh, sorry, Steve. My wife complains about this phenomenon all the time, and she doesn't blame the supermarket, but basically it's like, all right, you know, we've been cooking for ourselves for almost a year now during this pandemic, kind of sick of everything. You know, what are we gonna eat? What are we gonna eat, you know, this week, right? Let's make this dish. Okay, I need to buy A, B, C, and D in order to make this dish. And so then when they're out of D, it's like, well, shoot, if they don't have D, I don't want A, B, and C anymore either. And we don't expect the supermarket to magically know this, but it's like really annoying, you know. And so that's actually one of the reasons why I am not in any way advocating, but one of the reasons why she uses Instacart sometimes, even though it may be more expensive than some of the other options she has, is because then she actually will talk to a human being who will say, hey, you know what, they're out of, you know, Napa cabbage. It's like, well, the whole dish requires Napa cabbage. So then, you know what, don't even bother getting me A, B, and C. And they'll be like, okay, yeah, I can do that.
By the way, airplane tickets, they're oversold on purpose. It is built in. It is a feature. It is not a bug. And the thing is that I don't know what is their percentage, but theoretically it could work this way. In 95%, somebody actually doesn't show, but they have enough places. And once in a while, 5% once in 20 times, they got overbooking actual and cannot put a person on the plane. But it is cheaper for them to pay off this one person than to go with not sufficiently full plane in these 19 times.
Yeah, except for the few times when you have air marshals bludgeoning people and it gets captured on video and goes viral on the internet, right?
Well,
yeah, that's not in the percentage, I guess.
Yeah, and I was going to say, like, they definitely are recording the number of times they've oversold, what they had to do to compensate to during that oversell, and they build models. Like there's entire models about what this looks like. So
Yeah,
that's
yeah.
usually
Actually,
what drives it.
my company, you know, we schedule appointments, and there are places where cancellation rate's high enough that we purposefully overbook our clinicians, because it's like, well, if the cancellation rate's 30% and you can do 6 appointments, maybe we'll schedule 7, maybe we'll schedule 8, because odds are at least one person's going to cancel, you know.
And we were even talking about the same situation with vaccination. How many appointments that you should book so that you can maximize it? Because if you only book to the capacity, there's a share of that actually empty.
Yeah, I can't resist. I have a story. I think I've told this before, but I have a friend from college. He's a doctor and he works for a pharmaceutical company, and he deals with regulators on various drugs. And so they deal with all these different countries. And so, you know, he's told me that he'll do things like fly to Beijing for a 1-hour meeting. So like this huge international flight, you know, drive to the meeting, then like drive back to the airport, fly back to, you know, Chicago. So he had like 80 bajillion miles with whatever airline, you know, American Airlines or whatever. And so he actually shared with me that there is this status that I didn't know existed. But basically he earned this status where he doesn't even need to buy a plane ticket. He can just walk up to like the airport and say, I need you to put me on a plane to blah blah city, the next plane on blah blah city. And even if that flight is full, they'll be like, yes, sir. I mean, he's paying full price or whatever, you know, but basically they just say, yes, sir. And that, even if they didn't overbook that plane, it is now overbooked because he can just show up and say, I'm going to be on this plane. I thought that was pretty nuts.
Yeah, so Becky, I think at the end of the day, the short answer is it really just depends on the business, because there can be so many layers between them and the data. For example, you know, Amazon now owns Whole Foods that has warehouses, that has suppliers, et cetera, et cetera. So for Amazon to figure out when you're putting stuff in your cart, whether something is really available or not, they may need to go through several layers to figure that out. And so, you know, again, just comes down to business model. Some businesses allow overbooking, others don't. Others will reserve it only when you actually buy it. Others will actually reserve it after you buy it, before you buy it. It really just depends.
Yeah. And I want to say there's one other discrepancy that we usually overlook, is that the actual discrepancy between what the computer thinks the world, its worldview is, and what the actual worldview is. And it's like a lot of the time that will stay in sync, but to your point of like, if I put something in my cart online, that deducts it from their running inventory. If I'm in the store and I take something off the shelf and put it in my cart, it doesn't get deducted until I get to checkout, unless you're in one of the shop and go places. But so there's that where it's like, even if we try to account for everything that we can in the computer realm or in the data realm, we have this, you know, that's only a proxy for reality, right? So
Yeah, definitely. So I wonder though, like the I guess the bigger part of my takeaway from my own experience is more actually about expectation I'm now developing for kind of smarter shopping experience, right? Based on all these algorithms behind the scene. And I wonder if, I don't know if you guys or most people also have these kind of expectation kind of being elevated even more in the future. Like sometimes you just don't feel like, okay, I thought that we are at the time now that the systems and machines can figure out some of these things and can learn on its own about exactly if I need A, B, C, D to do my own whole thing. And if I don't have D, I shouldn't be needing A, B, C, that kind of thing. But I totally get it. I just think that it's kind of interesting to like, as the machines are catching up to our kind of real kind of experience and how much I can be disappointed if it is not delivering.
So Becky, what do you think about the idea of online sites offering explicit transactions just like databases do? So my wife could say, here's a grouping of A, B, C, and D ingredients that I want from the supermarket. I either want all of them or I want none of them. So if any of them is out of stock, then cancel all 4 of those. You can go with these other things, but would that just be way too confusing for the average person?
I think it may be for confusing for the average person, but I would like to still have the option. But anyway, I think it can be like a checkbox next to it or something like that.
Yeah, I mean, it doesn't have to be like in your face the default, right? But like if it's sort of this feature that you can create groupings of your purchases.
But if you think about it, the opposite side is already happening, meaning that, I mean, there are plenty of recommendation engines being used. Like, why are you recommending things to me if you think that I'm buying this and might need the other thing? But you don't know. You're saying that the system is not smart enough to know when I request this. And if you're taking something off that, and then you are thinking that I still want to keep the rest of it, right?
Yeah.
It's like the opposite. It's not a very satisfactory experience. But I think part of it is, like to Hobson's point earlier, is a profit maximization motive, right?
Right. Yeah. If most people just don't get all that riled up about it. But I was just thinking, there's lots of circumstances. You know, if you're buying like linens for your bed, like generally speaking, you're right. You're buying the different sheets separately. You're buying the pillowcases separately, and so like if they're out of stock on the sheets, I don't want the pillowcases.
Yeah,
right?
exactly. Those are logical things you would think, but anyway, and this is actually a pretty kind of high-end brand. You would think that they should kind of know to an extent. But anyway, this is not meant to be a distraction.
From the data science perspective, it's hard to estimate how many people are dissatisfied and never come back. It's hard to estimate what the cause is for customers that just don't come back, non-returning customers, because you have to wait years before you know that they didn't come back if people don't typically make a lot of purchases, and so people do, and so if a data scientist comes to their boss and says, I think these people aren't coming back because of X, because we're not reserving the product, he has a really high bar to get over, because there's a big expense in terms of all this data manipulation we're talking about, and indexing, and making sure your databases are up to date. And so it's a big expense in order to change your system to be more complicated, in order to try to make those reservations more, in order to eliminate perhaps someone who might have not come back if you had done it better.
And I think, Becky, it is totally not a distraction. Your question is the in-person equivalent of transaction management. Like what Hobson's saying, like being able to handle all of that from the standpoint of like, oh, sometimes we look at transactions like, oh, I have this begin, I have a commit at the end, right? And then some things happen in the middle. But realistically, it's like, oh, maybe it's spread across 4 different systems or 10 different systems. And it's just like having to think about that from an application scale. Like this, it's a perfect parallel from the, oh, how do we as people think about, transactions?
Yeah, but you're definitely getting me riled up. I'm thinking maybe I'll actually email people at Instacart and see if they would consider providing grouped items, grouped groceries as effectively transactions, right? For advanced, customers who actually want to say, only give me all of these ingredients or none of them. All right, so moving on, let's talk about some of the different phenomena, the race conditions that can happen and how people solve them. So the first one, the easiest one to solve, is called dirty writes. Okay, so this is where you have a transaction that's running, it makes a change somewhere, bank account 1, subtract 100. You're not allowed to then rechange the balance on bank account 1 until that first transaction has completed its transaction. Whether it committed or whether it rolled back, it has to finish everything. So basically, you are going to block. You are going to wait until whoever touched bank account 1, you're going to wait until they finish with everything that they're doing. It's not just waiting till they're finished with bank account 1, it's finished with everything that they're doing in their transaction. So this isn't really mentioned in the book. There's just a footnote. That's the only place where it appears. But so this is commonly called read uncommitted amongst vendors. And the implementation is pretty straightforward. So I gave this introduction to what locks are. And so you have a special type of lock here that's an exclusive write lock. And only one person is allowed to hold a write lock for any particular key at a time. So as soon as the first transaction starts and it's going to subtract 100 from bank account 1, it puts an exclusive lock on bank account 1, and then it goes and subtracts the $100. And then at that point, it holds onto that lock. It does not release it. It holds onto it, and it does all the other things. And so it may grab more locks as it's writing other things and doing other things. And however long it takes, it holds all these locks. And then at the very end, if the transaction commits, then all the locks are released. If the transaction fails and it aborts, then everything's rolled back and all the locks release. So that's how it's implemented. And I just wanted to comment that I actually use read uncommitted a lot because I'm mostly doing analytic workloads. And so, for example, if I have a database, a data warehouse server that I think almost all of the updates to it happen overnight, then when I'm running my queries during the day, I don't actually expect there to be any write activity happening. And so basically, you know, what I can do is I can tell you know, my query, I'm doing a bunch of selects. Just don't worry about locks. Just pull the data as fast as you can. I'm not worried about, you know, potential race conditions because generally speaking, nobody's writing to this data. It's the middle of the day. It's all read only. So I thought that was, at least for me, that's something where, you know, we run our, you know, we run standard queries where we basically say don't use locks. Any questions? Okay, so dirty writes is usually, you know, pretty straightforward to understand. Dirty reads, a little bit more complicated, but not too difficult to understand. So basically, this is the idea that somebody else, another transaction, can be reading and they can end up with a partial subset of your information. So the information in the book is, with the bank account example, if you read that bank account 1 has $100 less, but you don't actually get the part where bank account 2 has $100 more, then you might think that the total of all your bank accounts is less than it used to be because it got half the transaction, not the other half. The other thing that can happen is if this dirty read is something that eventually gets rolled back, then you can see this mysterious value that never ended up getting written to the database. And so I've had this happen to me occasionally where basically it's like a Twilight Zone moment. You know, it's like you go and you look at the database and it says something. It says like, you know, Becky bought, you know, a new pillow. And then you go back the next day and Becky has no purchases, and you look at the logs and it's like nobody has bought a pillow, and it's like, am I in the Twilight Zone? Am I crazy? But the issue is that if you have a dirty read, then basically you can see something, and if that errored in it and it rolled back, then it's not going to appear anywhere. It's not going to appear in the data. It's not going to appear in any of your logs, even if you have audit trails and everything. It's just, and so so that's why, generally speaking, all databases are going to at least enforced read committed, and read committed will prevent dirty writes and it will prevent dirty reads. So in terms of the implementation, it's kind of this funky thing. I had to think about it a little bit. You can use locks to implement it, but there's a lot of reading of data that happens in databases. Sometimes you don't have a lot of writing, but there's almost always a lot of reading that happens in databases. And so if you use read locks, what you need to do is, before you read any piece of data, you need to ask for a shared read lock. And what happens there is if somebody else has written to it, if they have one of those exclusive write locks, then you have to wait. If other people are reading it, no problem. You can also simultaneously be reading it. And so then once you've read the data, you don't have to wait till the end of the transaction. As soon as you're done reading it, you let go of that lock. Generally speaking, vendors don't implement that because there's so much read activity that would be a lot of lock activity. So instead, what they do is this implementation where only one person can be writing something at a time, because once you get an exclusive lock, you're the only person. And so if only one person can be writing a particular record at a time, that means that there can be at most two values, the before and the after. And so they just have to implement this special mechanism where at the same time that you're basically getting a write lock, the system's going to keep track of before you got the write lock, what was the value of this? And then you can go and you can change that value as much as you want. And then once you release the lock, if you're successful, then that becomes the permanent value. But in the meantime, anyone who's doing a read sees the value from before you obtain that write lock. So it's kind of this clever thing where basically you don't need multiple rows, you just need one extra value per item. So I'll pause again. Any comments or questions? All right, so I've done a ton of stuff with Microsoft SQL Server. Microsoft SQL Server by default is using read committed, and until reading this chapter, I didn't really realize that by only doing read committed, that everything else that's talked about later in the chapter, all these failure modes, all these race conditions are possible. And so I don't tend to, write like end user applications, but it really opened my eyes to, I easily could have written application code that allowed certain race conditions and just didn't realize it because I never really thought about transactions that deeply. So then the next isolation level up, it's a little bit harder to implement, but provides a little bit more guarantee, is snapshot isolation. There's this term repeatable read where the author basically says, don't use it because it can mean like at least 3 different things and people use it inconsistently. So snapshot isolation means more guarantee than just read committed. It means that you're going to get one consistent view of everything in the database when you run your query. And so, a simple example would be if you had a really long running query. So let's say you wanted to know what is the sum of every bank account, every single account that we have in the whole system, right? If that query takes you, hypothetically, 10 minutes to run, in those 10 minutes, various other things are going to be happening. And so you are not going to get a consistent picture. And so your sum is not going to be accurate. It's going to be very hard to interpret what does that really mean. It could be higher, it could be lower than what's the actual amount. And so snapshot isolation solves this problem of read skew. So that's where you're reading one thing and you're reading something else, and you're actually getting values from different points in time. So one way in this, in which this happens is when people do a backup of the database. We used to do backups and they would take hours. And so if you have a backup and the first thing it does is it backs up your customers table and it says Becky's done 1 purchase. And then 5 hours later, it finally gets around to backing up the orders table. And there are 2 orders for Becky because in the intervening 5 hours, Becky bought something. Then it's like, when you restore this database, it's going to be totally inconsistent. And so you need something like snapshot isolation so that you can say, I can back up the database before Becky bought something, and it can say 1 purchase and have 1 order, Or I can get it where it says Becky made 2 purchases and have 2 orders, but I can't have that mixed situation where it says she's only made 1 purchase, yet there's 2 orders in the order table. So to implement this is kind of a little bit more complicated. You still use write locks to prevent dirty writes, but now what you need is this special data structure where you're keeping track of every active transaction and everything that it's writing. And different readers, different transactions might start at different times. And so they have a different point in time that's sort of their reference point in time for that, what everything needs to be consistent with. So I'm looking, it's 118. So I start a transaction, I say read every bank account in the database. I'm going to get sort of the 1:18 p.m. point of view of what the value of all those bank accounts is. But if Ryan starts a transaction at a minute later at 1:19, he's still getting the guarantee of snapshot isolation, but the values that he sees for every bank account might not match the ones that I see. They'll all be internally consistent, but you need to keep track of multiple values for every, potentially for every record, in case you've got multiple queries, like my example with Ryan and me both doing big giant queries. So when I last checked, Microsoft SQL Server does not enable snapshot isolation. I think they call it repeatable read. It does not enable snapshot isolation by default. So this extra work of keeping track of these multiple copies, this MVCC, multi-version concurrency control, you have to explicitly turn it on and say, I'm willing to pay the extra overhead of having all these data structures. And that's whether or not the queries are even using snapshot isolation or not. But if you say, yes, sometimes I might be using it, then you have to turn it on for the database and it'll create all these extra data structures.
So Ted, I have a question there, specifically to SQL Server, because I didn't realize that. But so if you don't turn it on explicitly, does that mean that the backup that you do of SQL Server may be inconsistent?
That's a really good question. So by the way, if you try and run a query and you say, I want to use snapshot isolation, it'll say snapshot isolation error. Snapshot isolation is not turned on for this database. Okay, so it turns out that for database backups, they have to be consistent. So SQL Server uses a trick, which is that normally if I run a query at 1:18, then I say, I want a consistent view of what all the data was at 1:18, right? What Microsoft does for backups, and I haven't kept track, so it's possible the latest versions do something slightly different. What they do is they do this big old read of everything, okay? And things could be inconsistent because it's getting a later value of stuff that got copied later in the backup and an earlier value of things that got copied earlier. But they're taking advantage of this phenomenon that the backup itself might take 10 hours, but the amount of activity that happens in 10 hours is actually relatively small. So what they do is they back up all the data, even though it's inconsistent, and then they make a backup of the transaction log, the write-ahead log, of all the activity that happened. And so they say when you do a restore, what you have to do is you have to restore the raw data, which is inconsistent. And then you have to replay all the transactions that happened during the 10 hours of backupping. And theoretically, there's some sort of safeguard thing where if it took you 5 minutes to actually copy the transaction log, it's also then copying the 5 minutes of activity. And fairly quickly enough, you get smaller and smaller chunks so that basically it's able to copy the last bit of transaction log without, a lot of activity happening in the background while it's doing that.
Got it. Thank you. Okay.
Did that actually make sense?
Yeah, it does. Thank you.
Yeah. So I thought that was kind of clever. So if you do replication, it has to do snapshot copies and backups. It uses the same trick where instead of the point in time at the beginning of the backup, it's actually giving you a consistent snapshot of what was the point the data looked like at the end of the backup running. All right, anybody else?
Do you have time steps for each table backed? At what point of time it was backed up?
So actually, Microsoft does support, that's an extra special kind of backup. For a vanilla backup, it does not do that. But how it manages it is that the write-ahead log is a single log. And so it's like single leader replication, right? Where all writes go through this one log. And so they're always perfectly sequentially ordered. And so you know, and so you can always say that if I have a log between this time and that time, I have all activity that was committed by, let's say the backup started at 1 o'clock. If the backup finished at 11 o'clock, you can say I have an accurate picture of every write that was successfully committed between 1 p.m. and 11 p.m.
Okay, thanks.
Anything else? All right. And so then the other thing they talk about is these lost updates. So the simple example they said is, oh, 2 people are incrementing a counter. And so if the counter starts at 0, you could wind up with 2. That's what you normally want. But if you do something funky where you say, I read it, it's 0, somebody else says I read it, it's 0, and they both say set it to 1, then the counter is not actually going to be 2. So the things you can do to help, you can have atomic operations. So if you have an atomic increment, then it doesn't matter because you're not actually saying set it to 1, you're saying bump it up by 1. And so even though you might think it's 0, the bump it up by 1 operation is safe. And so the first one runs, it goes from 0 to 1. The second increment operation comes along. You might be thinking you're incrementing it from 0 to 1, but it doesn't matter. The database knows it's now 1, and when you say increment, it bumps it up to 2. So that helps. They show there's this syntax in SQL where you can say for update, and basically what happens there is there's a new type of lock now. So I talked about exclusive locks where only one person can have it. And I talked about read locks, which are shared where multiple people can read at the same time, but you can't necessarily read and write at the same time. And so then there's this update write lock that has slightly different behaviors, where basically you're saying, even though I'm not actually doing a write at the moment, I'm going to be doing a write later on. And so since I know I'm going to be doing a write later on, the update lock will prevent somebody else from going and doing a write. But it's a little bit more lenient in that it'll allow other reads to continue to happen in the meantime until you're actually ready to go ahead and do that right. And then they talk about, like, you can have compare and set operations. I think they also mentioned those CRDTs is a way that you can, but ultimately those help, but you can have certain use cases that are more complicated than that. And if that's what you have, then the best thing is some databases will build into snapshot isolation auto detection of lost updates. And so if you have that, you can turn that feature on. And so that might specifically, depending on your use case, if you're buying a database, you might, if you're concerned that that's going to be a problem with your use case, then you might want to specifically look for a vendor who supports automatic detection of lost updates. Otherwise, other than going to full serialized, you're going to, if you don't build it in with something like these atomic write operations or whatever, just merely using transactions will not guarantee avoidance of lost updates. Okay, so then the last pair of race conditions that they talk about are write skew and phantom reads. Briefly, basically, before we talked about what happens if 2 people are trying to write the same exact object. So both people are trying to update the balance on bank account 1, for example. How these differ is it's not that I want to write to bank account 1, but it's that I want to make a decision based on the things that I see in the database. And so I think the example, if I remember right, the example in the book they talked about is you must have a minimum of 1 doctor on call. So I just read the list of doctors to see who's on call. Is, oh, good, there's 2 of them that are on call. And so I'm making a decision. And ultimately what I end up doing is I end up saying Dr. 1 is no longer to be on call because Dr. 1's going to call in sick. But unfortunately, another process is running and it says Dr. 2 says, oh, there's 2 doctors on call. I'm going to say that Dr. 2 is no longer on call because they're on sick. And so now you have 0 and you violated this property that you wanted. But this won't get caught in the above examples because you're not actually writing to the same doctor. One of them is trying to write to Dr. 1, the other one's trying to write to Dr. 2. And you can just come up with ever more complex scenarios. There is no way to solve for all possible forms of write skew unless you have serializability. And so serializability, again, is where if you took the transactions, there is, you don't need to actually calculate what it is, but there's just, you can prove that there's the existence of some ordering of those transactions where if they happened one at a time, then the results would be the same as what you actually got when they were running concurrently. So then the last part of this chapter talks about how can you actually do serializability, which generally speaking, historically has been avoided because it's too expensive. So this was the 2 of the 3 things here were very new to me and I thought it was very interesting. So one option is go ahead and actually run them one at a time. So only have a single thread where you do your writes. And for an in-memory database, because in-memory operations are pretty darn fast, depending on your workload, if it's mostly a read workload and there's not that many writes, you just funnel all your writes to this one thread and it does all of them one at a time. And so then it's you don't have to worry about like, is it in, can you find a particular ordering? They are literally just done one at a time. The author also mentions anti-caching. So I thought this is pretty clever. So if you're doing things and then somebody says, I want to do this thing, and for whatever reason, it's not in memory, if you wait for it to come back from disk, that's going to be slow. An easier idea is you set that transaction aside, you basically error it. And then in the meantime, you say, go fetch that stuff that I need, the data I need to do that transaction. And in the meantime, you go and you process a bunch of other people. Because remember, the whole idea of serializability is not proving that whoever asked for something done first is first. It's just proving that things happen in a consistent way one at a time. So then you can go back and you can retry the application once everything's in memory. 2-phase locking is the standard way that's been done for the last 40, I don't know how many years, 50. And basically there, the idea is that you use your locks more aggressively. So in snapshot isolation, in read committed, writes don't block reads. Reads see a different version of reality. In 2-phase locking, writes fully block reads. So that means that if there is write activity going on, nobody else can either read or write the same thing that you're looking at. And so if you're Twitter and somebody's looking at some super popular person, you can't afford to have it where nobody else can read the information about somebody who has, 30 million followers. That's just untenable. So that's why full 2-phase locking and full serializability is not the default. It is not commonly used by people. And then this last section is serializable snapshot isolation. So really kind of cool. So optimistic concurrency. So instead of preventing problems, the guarantee it provides is I will be able to detect if there's a problem. And since these are transactions, you can always just safely redo the transaction if I detected a problem. So the idea there is that you use basically snapshot isolation in terms of how you're performing all this concurrent activity. And then it uses this algorithm that says, I will be able to detect if you did a stale read and then followed by some kind of write activity that then potentially could cause a race condition. Or it's going to say, I can detect if this transaction does a write that then affects prior reads that happened on other transactions, on other threads. And so as this guy's PhD thesis, he proved that all possible race conditions can be detected by checking for these two things. And so if you don't have too much write activity, what you can do is you can just allow all this stuff to happen, knowing there's the possibility of a race condition, but at least I will 100% of the time know that it happened. And then what I'll do is I'll just fail the transaction, and I can always start it over again now at a later point in time and hope that this time it won't hit a race condition and it'll be successful. And so I think that for a vast majority of workloads, an algorithm like this can work, because optimistic, you actually don't run into these race conditions that often. And so if it's very rare that it happens, then you're almost never failing things. And if you don't ever fail them and retry them, then there's not much of a performance penalty. All right. So I feel like I maybe rushed a little bit at the end there, but so that's chapter 7. Those are the different race conditions that we can have that cause problems, the different algorithms and implementations. If you're not really, the kind of person who's going to be implementing one of these systems, again, the takeaway from the author is, don't just assume that you bought this database system and it's going to take care of everything for you beneath it. You have to understand what isolation level it's offering, and you need to explicitly employ transactions in your queries, in your data access patterns. And depending on your workload, you may be worried about needing a stronger isolation level than just the default one when you say create new database. All right. Any questions, thoughts?
Just I thought that SQL looked much more reliable before this book.
Yeah, I was pretty naive. I thought it was, had much better guarantees. I didn't realize it's not that strong a guarantee.
That was what I was
Marketing, right?
It gets worse if you have to consider. I mean, this touched on some things from the standpoint of like, oh, SSDs can have write caches and this and that, but like there are things that crop up all the time. Just like a year ago, they've discovered a latent bug in the Linux kernel that basically left some writes not flushed for like Postgres that had been there for like 5 years, but like it rarely ever see it. And it's like, oh, great. So yeah, it's there's a lot of layers and a lot of edge cases that can happen.
Yeah, I will add that having used Microsoft SQL Server for a long period of time, there was a point where we ran into a problem where we were getting incorrect results in one of our reports. And we dug and dug and dug, and then finally we found a Microsoft, I forget the name of it, but basically a tech report that basically says there's a known bug in SQL Server where if you write this type of query, then SQL Server may return incorrect results. And I was like, whoa, like I know that there's like performance issues and there's other things that people complain about, but I didn't know that there were known bugs where it's just flat out returning incorrect answers. And we had a heck of a time because it was this really weird thing. And so it's like, I wrote a perfectly valid select and SQL Server just gave me like values that are not the actual values on the database. Like, what am I supposed to do? How am I supposed to work around this? So that's a different issue than just these other things, but that's, you know, just even further compounding the problem. Ryan, I don't know if your connection glitched. Were you going to say something earlier?
I was just going to mention the same thing as everyone else. Is it seems like these databases have been around for a long time, and it seems like based on what we've heard from this book, there's still techniques being developed that are kind of closing some glaring issues with some of these systems. It's kind of impressive that people have been able to kind of manage along with all of this stuff, given that it seems like not all of this is entirely built in necessarily.
Yeah, I mean, it's pretty weird, you know, like they gave that example of two people try to buy a car and it says Sally got the car, but Bob got the invoice or whatever. It's possible that for years people have been writing applications, and once in a blue moon that happens, and then, you know, a report goes in, some poor developer's like, I don't know, things look okay, and they try and reproduce it. They can't reproduce it, and probably that bug just goes down forever as wasn't able to reproduce.
Yeah, it was just too rare.
It was too rare, and so nobody ever figured out that it was actually because your database was read committed and didn't actually like prevent this race condition that you didn't think was going to ever happen.
Yeah.
Yeah, and that's on top of the fact that, you know, I come from like a relational database world. Some of these NoSQL databases, they don't even claim to have these protections, you know? So they say, oh, we're doing, you know, replication, and if a write errors, then some of the replicas that got that partial write before it errored out, we don't undo it. We don't roll it back. Just hope that's not a problem. Wow. So this is, yeah, this is even sort of like when you don't have any of those even lesser guarantees. So yeah, so that was kind of eye-opening for me. It's good to know. And again, yeah, you probably need to know this in and out if you're going to actually like work on, you know, work for building one of these products. But I think there's a really good buyer beware message for people who are even just buying a product, or fine, you know, we have Oracle, I have a database, what configuration settings do I need to turn on? And if I don't turn them on, then what extra hoops do I need to jump through to try to minimize these weird things that can happen if we actually are fortunate enough to have lots of customers, lots of concurrency. All right, so I spent a lot of time trying to think about chapter 7 this week. I have not really successfully read ahead. I know that chapters 8 and 9 talk about problems. So at sort of the bigger scale, 8, it's sort of like what things can fail and what other worries do you have now? How much more sleep are you going to lose? And then I think chapter 9, I think, is then about like how do we try and coordinate, so like consensus and things like that. But so that's what's coming next. Anything else for anybody?
This is really clear. Thank you.
Thank you.
Yeah, awesome. All right, so then I think we'll call it a wrap, and then we can transition to the project and Kaggle stuff.
Sounds good.
Great,
Thanks.
thank you.
Thanks. Bye.
Bye-bye, everyone.
Thank you, Ted.
All right, so you can stop the recording, Ryan. I don't know if you